Have you ever wondered how materials deform when stretched or compressed? This is where Poisson's ratio comes into play. It's a fundamental property of materials, a crucial piece of the puzzle that helps us understand how objects behave under various forces. But what exactly is Poisson's ratio? Well, it describes the deformation behavior of a material when subjected to a tensile or compressive force. In simpler terms, it's a measure of how much a material changes shape when we stretch it or squish it. Imagine a rubber band. When you stretch it, it not only gets longer, but also thinner. On the flip side, if you were to compress a sponge, it would get shorter, but also expand outwards. This phenomenon of becoming thinner when stretched and thicker when compressed is quantified by Poisson's ratio. In the realm of mathematics, Poisson's ratio, often denoted by the Greek letter nu, is defined as the negative ratio of transverse strain to axial strain. Put simply, it's the ratio of how much the material shrinks or expands sideways to how much it stretches or compresses lengthways. Interestingly, the value of Poisson's ratio varies between different materials and typically ranges between -1 and half. This range isn't arbitrary, but a consequence of the physical limits of material deformation. Some materials even possess unusual properties, allowing them to theoretically exceed these limits. Understanding Poisson's ratio is not just a theoretical exercise. It has practical applications in various fields, from engineering to materials science and biomechanics. It aids engineers in designing structures and materials that can withstand deformation and stress more effectively. Now that we know what Poisson's ratio is, let's delve deeper into its mathematical formulation. In the next segment, we will break down the equation, explore its components, and understand how it applies to the real world. So stay tuned as we continue our journey into the fascinating world of material science. To understand Poisson's ratio thoroughly, we need to take a look at the math behind it. So let's roll up our sleeves and do just that. The mathematical formula for Poisson's ratio, represented by the Greek letter nu, is actually quite straightforward. It's defined as the negative ratio of transverse strain to axial strain. But what does this mean? Let's break it down. Strain, in the world of materials science, is a measure of deformation representing the displacement between particles in the material body. Axial strain, denoted by EEA, refers to the change in length along the axis of the force applied. Transverse strain, denoted by EET, on the other hand, refers to the change in dimensions perpendicular to the force. Now, when a material is subjected to a force, it deforms. It stretches or compresses along the force's direction, and simultaneously, it contracts or expands in the directions perpendicular to the force. This simultaneous deformation is what Poisson's ratio is all about. So when we say nu equals sign, we're essentially quantifying this deformation. The negative sign indicates that the transverse strain and axial strain are in opposite directions. If the material is stretched, it becomes longer axially and contracts transversely. If it's compressed, it shortens axially and expands transversely. And what range of values can Poisson's ratio have? Well, for most materials, Poisson's ratio typically lies between -1 and 0.5. But why this range? It's because materials usually contract transversely when stretched, positive axial strain, and expand when compressed, negative axial strain. And while the value can theoretically go beyond this range for certain materials with unusual properties, these are exceptions rather than the norm. In general, materials with a high Poisson's ratio tend to be ductile like rubber, while those with a low ratio are brittle like chalk. So that's the math behind Poisson's ratio, but why is it so important? Well, this humble ratio plays a crucial role in many fields, including engineering, materials, science, and biomechanics. But more on that in the next part of this series. Stay tuned. Poisson's ratio is not just a number. It's a key player in various fields, from engineering to biomechanics. This fascinating concept has a significant impact on the world around us, influencing everything from the design of skyscrapers to the resilience of human tissue. Let's start with engineering, a field where Poisson's ratio is a fundamental player. When engineers design structures, they need to consider how materials will deform under stress. Will they buckle or bend, stretch or compress? The answer to these questions lies in the Poisson's ratio. For example, materials with a high Poisson's ratio like rubber are less likely to break under tension, but may deform more. On the other hand, materials with a low Poisson's ratio like cork are more resistant to deformation but may fracture more easily. In addition to structural engineering, Poisson's ratio is also crucial in the design and selection of materials for various applications. Consider the automotive industry, where materials need to withstand high stresses without deforming. A car's body, for instance, needs to be rigid enough to protect its occupants, yet flexible enough to absorb impact during a collision. Understanding the Poisson's ratio of different materials helps engineers strike this delicate balance. Poisson's ratio also plays a vital role in biomechanics, the study of mechanical principles as they apply to biological systems. For example, consider the human skin, which has a high Poisson's ratio. This enables our skin to stretch and compress without tearing, making it incredibly resilient. Similarly, the low Poisson's ratio of bone tissue allows it to withstand high compressive forces, such as those experienced during running or jumping. And let's not forget about the world of sports. The Poisson's ratio of a tennis ball, for example, affects how it bounces and spins. A higher Poisson's ratio means the ball will deform more upon impact, resulting in a higher bounce. Conversely, a lower Poisson's ratio will result in a lower bounce but a greater spin. As you delve deeper into the world of materials science, you'll find that Poisson's ratio pops up in the most unexpected places. From the elasticity of spider silk to the rigidity of concrete, this humble ratio has a profound impact on the world around us. It's fascinating, isn't it? A seemingly simple concept, yet so incredibly powerful, but that's the beauty of science. It offers us new ways of seeing and understanding the world, often in ways we never could have imagined. As you can see, Poisson's ratio plays a critical role in our daily lives, often without us even realizing it. It's a testament to the remarkable complexity of our world and a reminder of the wonders of science and engineering. Whether you're an aspiring engineer, a curious mind, or just someone who loves to learn, understanding Poisson's ratio can offer a whole new perspective on the world around us. Let's take a moment to recap what we've learned about Poisson's ratio. We've embarked on an enlightening journey through the realm of materials science, focusing on this fundamental property of materials that describes how they deform under tensile or compressive forces. We started by introducing the basic concept of Poisson's ratio, which quantifies the relationship between the transverse strain and the axial strain when a material is stretched or compressed. We learned that when a material is stretched, it tends to become thinner in the transverse direction and longer in the axial direction. On the other hand, when it's compressed, it becomes thicker in the transverse direction and shorter in the axial direction. Then we delved into the mathematics behind Poisson's ratio. We defined it as the negative ratio of transverse strain to axial strain, expressed as nu equal sign ET plus EA. We also discussed that the value of Poisson's ratio typically ranges between -1 and 0.5 for most materials, but can theoretically extend beyond this range for certain materials with unusual properties. Afterwards, we explored the importance and applications of Poisson's ratio. We discovered that understanding this ratio is crucial in many fields, including engineering, materials science, and biomechanics. It influences the design of structures and materials, helping them to withstand deformation and stress more effectively. We also discussed how materials with a high Poisson's ratio are more resistant to bending but may be less stretchable, while those with a low Poisson's ratio are more stretchable but may be prone to buckling under compression. And that's a wrap on our exploration of Poisson's ratio. Remember, the world of materials science is vast and fascinating, and Poisson's ratio is just one piece of the puzzle. So continue to explore, continue to learn, and stay curious about the world around you. There's always more to discover, and every piece of knowledge adds to the bigger picture. Thanks for joining us today in our exploration of Poisson's ratio. We hope you found this journey through the world of materials science both enlightening and engaging. If you've enjoyed delving into the intricate relationship between axial and transverse strain, please don't hesitate to give this video a like. Your support truly makes a difference. If you're eager for more, subscribing to our channel is the best way to stay informed about our latest content. We regularly delve into a wide range of fascinating topics, from the fundamentals of engineering to the mysteries of the universe. There's always something new and exciting to discover. Remember, the world around us is a treasure trove of knowledge waiting to be uncovered, so keep that spark of curiosity alive, keep learning and keep exploring. The more we learn, the more we realize how much there is yet to understand. Until next time, keep exploring, keep learning, and stay curious. Take care.